Welcome back. This lecture is on one sample t-tests. This lecture really builds on the uh, lectures that we've had before. So the one sample t-test is really just an extension of the z-tests that we've already learned. But it's useful in a couple situations that are more practical and realistic in everyday research. So in most of the cases that we've covered so far, we've known population parameters. Specifically, when working on the z-test, we've known a population mean, mu, and we've also known the variance and the standard deviation in the population. In reality, we typically don't know these values because we only have data from our sample. We've previously learned that we can estimate a population mean mu using a sample mean. We're just going to extend this logic, and now we're going to learn that we can estimate the variance in the population as well as the standard deviation using the variance and standard deviation that we calculate in our sample. So just notice the different terminology. We've got a sigma squared and a sigma to represent the population parameters for variance and standard deviation. And then we've got SD squared and SD to represent the descriptive statistics that we would calculate for variance and standard deviation using sample data. So a one sample t-test is a hypothesis testing procedure in which the population variance is unknown and therefore it is estimated from the variance that we calculate using our sample data. It's very much like the z-tests that we've already learned, but instead it compares a t-score rather than a z-score from a sample to a comparison distribution, which is called the t-distribution. So we have previously been working with the standard normal distribution. This is a bell-shaped curve, and it has several properties. It's symmetrical, and we know that there's a set percentage of scores that fall between any two z-scores or above a certain z-score. Well, a t-distribution is very, very similar. It just has some slightly different properties, which we'll learn about in just a little bit. So sometimes this t-test is called the student's t, and this is after the person that created the statistic. This is written up in the chapter, but it turns out that the person that created the statistic worked for the Guinness Brewery and was doing statistical tests to try to calculate things like crop yields for barley. And so the statistics that he developed ended up being the essentially industry trade secrets of the brewery, but he knew that the statistics that he was coming up with were so valuable, he wanted to publish what he was doing, and so he published under an alias, which was student. And so this is, the t-tests are often called student's t. Oh yeah, there we go. All right, created by William Gossett. All right, so let's just get into a concrete example, and I think this will be a really good way to learn the t-test and how it's slightly different from the z-test. But if you're familiar with the z-test, you should pretty much be able to do a t-test. We're going to follow all the same steps of hypothesis testing that we've already learned. All right, so here's an example. Suppose that we're researchers and we are interested in understanding students' attitudes about underage drinking. Specifically, we want to know how acceptable or unacceptable Miramar College students find underage drinking. We create a questionnaire item asking students to rate the acceptability of underage drinking on a 7-point scale, where 1 is extremely unacceptable, 2 moderately, 3 slightly, 4 neutral, 5 slightly, 6 moderately acceptable, 7 extremely acceptable. So there's a range of attitudes that could range from 1 to 7. We're going to administer our questionnaire to 10 Miramar students that have been randomly selected from the student body. So simple example, just to keep the numbers simple, we're going to have only 10 students. In order to make conclusions about a population based on sample data, we have to do an inferential null hypothesis significance test. So our sample only has 10 students, but we're interested in making an inference to the entire population, okay, all students. Before we analyze our data, the way that null hypothesis significance testing is supposed to happen is to specify a research hypothesis and a null hypothesis and set up a critical value in advance. So that's basically our step 1, 2, and 3. Okay, so we have to think about what it would be the research as well as a null hypothesis if we want to be able to determine whether Miramar students find underage drinking acceptable or unacceptable. The way that this is done in practice is to test sample data against a neutral point, often the midpoint on a response scale. So let's take a look at the question that we asked as well as the response scale. This response scale could range from 1 to 7, 1 being extremely unacceptable, 7 being extremely acceptable, and the middle point is 4, which represents a neutral attitude, not feeling one way or the other, not feeling that underage drinking is unacceptable and not feeling that it's acceptable. So that neutral point becomes a way to kind of what would be consistent with a null hypothesis. So if we want to know whether our population of Miramar students feel one way or the other, that is, do they think that drinking is acceptable or do they think that it's unacceptable, we can test an average attitude against that neutral point. So the inference is that we're statistically testing whether our sample is drawn from a population with a neutral attitude versus a population that believes drinking is either acceptable or unacceptable. In other words, has an opinion one way or the other. So our research hypothesis is essentially that on average, Miramar students will have an attitude, that is, they have a non-neutral attitude. And we're going to test against that midpoint of the response scale. So to restate, our first step with hypothesis testing is to restate the problem as hypotheses about populations. Our first population, in keeping with the convention that population 1 is the treated population or the population that receives an intervention, we can think about population 1 here as being the population of interest. We somehow think that Miramar students are different than this null population. So by convention, they end up being population 1. Whereas population 2 is the population that is associated with the null hypothesis. That is, they have a neutral opinion. So our research hypothesis would be that Miramar students are different from other people in their attitudes. Miramar students believe drinking is either acceptable or unacceptable. Okay. And so what we need to do is come up with a specific value, and we'll use the value of 4 from the questionnaire, which represents a neutral attitude. And what we're saying is, on average, Miramar students would have a mean that is different than 4. We aren't predicting whether they're going to have an attitude about drinking which is favorable or unfavorable, that they think it's acceptable or unacceptable. We're just saying it's different than neutral. So notice that we have a two-tail hypothesis here. Our null hypothesis is that Miramar students are the same as other people. They also have a neutral opinion. Okay, so mu equals 4. So one thing that you could kind of have, and this is what I like to do when I think about these research hypotheses at the level of populations, is I often have those figures in my head, like those two curves, and I think about a distribution of attitudes centered around a mean of 4. Okay? Means that at a level of a population, some people find drinking acceptable, some find it unacceptable, but we're saying that on average, the average in the uh, comparison population is 4, a neutral attitude. Okay, so that's one population. And then our population of Miramar students, if the null hypothesis is correct, is basically directly overlapped onto that comparison population. So you could think, now we don't know whether attitudes are normally distributed, but for the sake of simplicity, let's just say that they are. You could think about two bell-shaped curves that are centered around 4 and are overlapped on each other. Okay, so that's what's kind of our, under the null hypothesis, that is what is happening at the level of population. Okay, so the second would be to determine characteristics of the comparison distribution. So we know under the null hypothesis that we're kind of assuming that the mean for our comparison population is 4, a neutral attitude. But we don't know what the variance in this population would be. Okay, so that's a little bit of a problem. And we know that this is a problem because we know that we need to get the population variance, sigma squared, in order to determine the variance of the distribution of means, which will give us the standard deviation of the distribution of means, otherwise known as the standard error of the mean, right? So that sigma m is the standard error of the mean, and what that tells us is the average amount that any mean could differ from 4 just by a random sampling process. Okay? So again, really make sure that we're comfortable with the definition of standard error and what that conceptually means. I'll give it to you one more time. When we talk about standard error, we're talking about, on average, how much any particular sample mean that we randomly sample could differ from 4 in this case. All right. So we know via Rule 2a and Rule 2b of the central limit theorem that we calculate standard error by first starting with the population variance, dividing the population variance by n, getting the variance of the distribution of means, and then getting the square root in order to get the standard error. So we've got a problem because we don't know what the population variance is. But here's the solution. If a sample is taken randomly from the population, the variance of that sample should reflect the variance of the population. Okay, and this should be a fairly straightforward assumption, is that if we take a random sample, and in this case we took 10 people, we can look and see how much variance is in that sample. And the variance in that sample should be some indicator of how much variance there is in the population. So if a population has a lot of variability, we'd expect that the sample would reflect that. And there would be a lot of variability in the sample. If a population has only a little bit of variability, you'd expect that the sample should reflect that as well, and there'd only be a little bit of variability in the sample. So therefore, we can estimate the variance of the population based on the variance that we calculate in our sample. Okay? And this is just a graph from the text that reflects that. So we can see that the sample would be the panel on the bottom, and each one of those samples has a certain amount of spread around the mean, right? So there's variability. And so that variability, we can either calculate a variance or a standard deviation to represent that variability. But the idea would be that the variability in the sample should be reflective of how much variability there is in the population. Okay, and so each one of those figures, A, B, and C, reflects kind of differing amounts of variability in a population that would be represented in a sample. Okay. Now there is one slight hitch to this, which is that a sample's variance can't be used directly as an estimate of the population variance. Sorry. The reason is because it can be shown mathematically that a sample's variance will, on average, be smaller than its population variance. Okay. So before, we had calculated the sample variance as the sum of the squared deviations from the mean divided by the number of participants in the sample. So hopefully we remember this equation, right? That the variance of a sample is the sum of the squared deviations from the mean divided by the number of observations or the number of people. This formula gives us a biased estimate of the population variance because it underestimates how much variance there is in a population. So that is, if we take the sample of 10 Miramar students that we're using in this example, and if we calculate the variance among those students, that number that we would calculate would underestimate. In other words, it would be too low of an estimate of the population variance. Okay, and that's for our purposes, we'll just say that that's true. That's been something that has been mathematically determined. We'll not go into the reasons for that, but it is a true property that if we want to estimate the population variance and we use our sample variance as an estimate, that sample variance will generally be too little or too low. It's an underestimate of the population variance. So what do? All we have to do is modify our formula slightly. Okay, so instead of dividing by n, we just divide by n minus 1, and that's it. It's the exact same formula, it's just modified by using n minus 1 instead of n. By dividing by a smaller number, okay, instead of n minus 1, so instead of by 10 minus 1 is 9, this will make the estimated variance, I say standard deviation here, but it will make the estimated variance, standard deviation or variance, larger. And it turns out that it's mathematically just large enough to be an unbiased estimate of sigma or sigma squared. I left out the exponent here, but all right. One thing I'll point out here too is you'll also notice a subtle change in the notation. What we're now using as an estimate of population variance is S squared. So previously we calculated standard deviation and variance as SD squared and SD. We're changing the notation slightly. We're dropping that D, and we're just going to use as our estimate of population variance S squared. And that conveys that we're no longer dividing by n, we're dividing by n minus 1. There's a name for this n minus 1 quantity, which is called degrees of freedom. All right, degrees of freedom is something that it's a term and a concept that will appear for the next several lectures. So it's important to get comfortable with what it is. But in most cases, degrees of freedom is simply calculated as n minus 1, or the number of observations minus 1. This refers to or reflects the number of scores that are free to vary. And in this case, there are n minus 1 degrees of freedom because when figuring out the variance, each score is subtracted from the mean. And thus, if all the deviation scores but one are known, the last score can have only one value. Okay, so there are 9 degrees of freedom because once you figure out 9 of those deviation scores, the 10th one is locked in place. All right. So we could go much deeper into that, but for our purposes, it suffices to know that degrees of freedom is a concept, and in most cases, at least with the t-test that we'll be using, it is calculated as n minus 1. All right, so therefore in this case we have n minus 1 degrees of freedom. Okay. So our formula for our estimate of population variance can be rewritten as the following. Instead of n minus 1, we're just going to use a shorthand and put degrees of freedom in the denominator. All right. Notice too that there's another shorthand which, instead of writing out the numerator as x minus m squared, the sum of x minus m squared, we can simply use SS, or sum of squares, the sum of the square deviations from the mean. Okay, so our second step is to determine the characteristics of the comparison distribution. Again, we know that the population variance for the comparison population, the population mean, mu, for the comparison population is 4. Our estimate of sigma squared will be based on information that we get from our sample. All right. So the way that this would be done in practice is to go and actually collect our data and to have our random sample of 10 students. Here's their answers to the questionnaire, which recall could range from 1 to 7, 1 being extremely unacceptable, 7 extremely acceptable. We've calculated a mean, and then what we can do is calculate a standard deviation. So I've set this up the way that we've previously learned how to calculate a standard deviation, just to show you that it's no different. We're going to do that by first taking the deviations from the mean, squaring those deviations. We're going to sum those deviations. The only change is that instead of dividing by n, we're going to be dividing by degrees of freedom. Okay, so here's what that looks like. We take our deviations from the mean. Okay, so just for this first one, you can see that because our mean is 5, 2 minus 5 is negative 3. Second one, raw score of 3 minus 5 is negative 2. And all the way down, I won't go through each one. We're going to square each one of those deviations. All right, so negative 3 squared is 9, negative 2 squared is 4. So we just repeat that process. We get all of our squared deviations. The next step is we're going to sum those deviations. I've just summed this column of data. So we get 26, which is the sum of the squared deviations from the mean, or the sum of squares. And then everything up to this point has been exactly the same as we've learned how to calculate a standard deviation. The only change is that now we're going to divide by n minus 1, which is 9. So we have 10 scores. Instead of dividing by 10, we're going to divide by 9. And so that's going to give us a variance of 2.89. Okay, notice that instead of SD squared, I've got S squared. Okay, this really should be an exponent, but I just got lazy and didn't make an exponent there. Okay, so that should be a superscript. Okay, so what is this telling us? This is telling us that our estimate of the variance in the population is 2.89. And we just used our sample data. We used the variability of our sample data as a way to come up with an estimate of what the variance in the population is likely to be. So now that we know S squared, this becomes our estimate of sigma squared. Okay. And then we can come up with the characteristics of our comparison distribution. Our hypothesis test involves a distribution of means. So we need to figure out the variance and the standard deviation of the distribution of means. Okay? This is exactly the same as a z-test. Exactly the same as a z-test. And if the logic or the reason why our comparison distribution is a distribution of means, I would strongly advise to go back to the previous lectures as well as the textbook and make sure that you understand the logic of why our comparison distribution is a distribution of means. All right. So previously, by Rule 2a, we calculated the variance of the distribution of means as the variance in the population divided by n. Now, we're going to do that same thing. We're just going to change our notation. It's the exact same calculation, only instead of using sigma squared, we're going to use s squared. Simply to make it very clear and very explicit that we didn't know what the variance in the population is. We're using an estimated value. It's also very important not to get confused. Notice that this is just n. Okay, this is n. That n minus 1 procedure, we used it one time, and now it's done with. It's completely over with. So once we have used the n minus 1 procedure to come up with an unbiased estimate of the population variance, we no longer need to use that n minus 1 correction. It's done, it's over with. Okay? So all of our formulas are exactly the same. It's just the notation is ever so slightly different. So we can calculate the variance of the distribution of means, and then from the variance of the distribution of means, we can get the standard deviation of the distribution of means. In other words, the standard error. And it's that standard error that we're really interested in, because that will be the bottom or the denominator of our test statistic, just like with our z-test. Okay? So before we used sigma subscript m, we're now just using s subscript m. It is the exact same interpretation. It is a standard error of the mean. That is about how much we expect any particular mean that we could sample from a population to differ from the expected value of 4. Exact same interpretation. All right. So, substituting into our two equations, our two formulas, we can determine that the variance of the distribution of means is 0.29. Okay, I just got that by dividing our estimate of population variance, 2.89 by 10. And then we can figure out that the standard error is 0.54, which is just the square root of the variance. Okay, so calculations that we should be familiar with. Okay, so this is one other kind of difference between moving from a z-test to a t-test. Previously, we were able to use the standard normal distribution as our comparison distribution. Okay, we knew that the distribution of means would follow a standard normal distribution. However, when using estimated population variance, we have less true information and thus more error in the resulting sampling distribution. Okay, so the central limit theorem can be used, and we know that because of the central limit theorem, we get a standard normal distribution when the population variance is known. However, if the population variance is not known, but we need to estimate it, and we engage in a random sampling process and sample all possible means from that population with unknown variance that we had to estimate, there's going to be more error in the resulting distribution of means. Specifically, what happens is that we'll get more extreme scores, that is, more means that are either very high or very low, and that will be especially true when we have small sample sizes. So when we base a random sampling process on a small number of people. Okay. So whereas previously our distribution of means followed a normal distribution, now our distribution of means follows a t-distribution. Notice that a t-distribution is very similar to a normal distribution. It's unimodal, with the mode being equal to the mean. It's also symmetrical. However, the major difference is that the tails of the distribution are fatter. We can say that there's a fatter tail on each end. Okay? And so because of that, all of the z-scores that we previously used, 1.64, negative 1.64, plus or minus 1.96. We've also used plus or minus 2.58, okay? And that there was a known percentage of means that would fall above and below all of those points. Those values go away. Those are out the window because the same percentages don't apply with a t-distribution. All right. So our t-distribution is this mathematically defined curve, and we're going to use it as our comparison distribution in place of the normal distribution when we're doing a t-test instead of a z-test. It turns out that there is a different t-distribution for each degree of freedom. So degree of freedom comes from our sample size. It's n minus 1. So for every different sample size that we have, we've got a different shaped t-distribution. The t-distribution starts to look more normal as n increases. All right. And by the time n gets to 30, the t-distribution and then looks just like the normal distribution. Okay. So in order to determine our cutoff for rejecting HO, the trick now is we've got a different lookup table. We're no longer going to use the standard normal distribution, and we're no longer going to use the lookup table of z values, but we've got a different lookup table. Okay, so given that we have the t-distribution is different for each degree of freedom, we're going to use a new table, which is called a t-table, and that's going to give us a critical value for each different degrees of freedom that we have. Recall from the way that we set up our hypotheses in this example that we have a two-tailed test. Previously, when doing a z-test, we always used plus or minus 1.96 with a significance level of 0.05. And that was all the time. Whenever we were doing a z-test, if we were doing a two-tailed test at alpha 0.05, we always used the critical values plus or minus 1.96. Okay. Now what we need to do is look up the appropriate critical value or values based on the appropriate degrees of freedom. In our example, because our sample was 10, we've got 9 degrees of freedom. Okay, so here's what a t-table looks like. What you can see is that the left-hand column is all of the rows are different degrees of freedom. Okay, so here's where we are. We've got 9 degrees of freedom based on our sample of 10. And then we've got kind of two different sides of the table, a side for doing one-tailed tests and a side for doing two-tailed tests. Based on our example, we're doing a two-tailed test because we wanted to know whether the average attitude among Miramar students was different than neutral. We didn't specify whether it would be acceptable or unacceptable. So we're using a two-tailed test. By convention, we'll stick with the alpha of 0.05. We want to do a significance test at the 0.05 level. But you can see that there's values if we want to be more stringent. We want to lower that alpha and have a more stringent or difficult critical value to surpass. You can also go more lenient and have a more relaxed alpha level. But by convention, especially in psychology and other social behavioral sciences, we use an alpha level of 0.05. Okay. So all we need to do is determine what's our degrees of freedom. Are we doing a one-tailed test or a two-tailed test? What's our alpha level? Based on those three pieces of information, the type of test that we're doing, degrees of freedom, and alpha level, we can just locate the appropriate critical value. Now notice here that we're doing a two-tailed test, but we just have the positive value. We should recognize that this means that we've got a critical value of positive 2.262 as well as negative 2.262. Okay, just like the plus or minus 1.96, we've got plus or minus 2.262. All right, so those are our critical values for our two-tailed test. So when we do our t-test, we're going to need to get a t that we calculate that is either more positive than 2.262 or more negative than negative 2.262 in order for us to reject the null hypothesis. Now what we can do is figure out our sample's score on the comparison distribution. This is the same as before, but instead of calculating a z-score based on doing a z-test, we're now going to figure out a t-score based on a t-test. Okay? And again, you can see the parallel between the two. Previously, sample mean subtracted the mean of the distribution of means divided by the standard error. All that becomes is the t formula with the exact same components, basically. Is we've got the mean difference divided by the standard error. So the formula is conceptually the same. And in essence, all we're doing is figuring out how much did our mean deviate from the expected mean under the null hypothesis in the metric of standard errors. How many standard errors away from the expected mean was our mean? And that's the exact same interpretation as a z-test as well. So it's very much the same. Okay. So recall, if you can go back several slides to the raw data, we had calculated that our sample mean was 5. Recall that our test value, the mean under the null hypothesis was 4, and that we had figured out the standard error is 0.54. And if you need to refresh yourself on where these numbers came from, just go ahead and pause the video and scroll back through the lecture slides. Okay, so from here we just work through the calculations and we get a t of 1.85. Oops, my animation's a little bit messed up, that's okay. So we're going to decide whether to reject the null hypothesis. Okay, our critical cutoff score was plus or minus 2.262. We calculated a t-score of 1.85, and therefore we're going to fail to reject the null hypothesis, which also means that we fail to find support for the alternative hypothesis that Miramar students do not find underage drinking acceptable, or do find underage drinking acceptable or unacceptable. All right, so here's the population distribution under the null hypothesis, okay, with a mean of 4 and an estimated variance of 2.89. Here's the distribution of means that is likely to result via a random sampling process from this distribution. Okay, notice that distribution of means would be centered around 4, which is the exact same as the population mean, and would have a standard error of 0.54. Okay, again, that 0.54 refers to one standard deviation in this distribution of means. Okay, so a standard deviation in a distribution of means is a standard error. They are one and the same. Okay. So what did we determine? Our mean of 5 would fall about there in the distribution of means. It would fall 1.85 standard errors away from the mean. And that is not far away enough for us to conclude that that at a population level, Miramar students have an attitude that is on average different than 4. Okay, so a sample, 10 students could be sampled from this population and get a mean of 5, and that is not so unusual at all. Okay, so that's very probable, even if the null hypothesis is true. Okay, so we don't have enough evidence here to reject the null hypothesis. So we're going to fail to reject the null, which means that we don't have support for our alternative hypothesis that Miramar students either find drinking acceptable, in other words, they'd be somewhere over here, or they would find it unacceptable, they'd be somewhere over here. Okay, not enough evidence to make a conclusion at the level of population that the true mean would be somewhere over here or somewhere over here. Yep, there's our t. Good. Right. P greater than 0.05. That is a test statistic, a t-score, that happens more than 5% of the time even if the null hypothesis is true. All right, just to review decision errors, is there a decision error that we could have made in this case? Could we have made a type 1 error? Why or why not? Think about that for a minute. Would it be possible to make a type 1 error? What about a type 2 error? Could we have made a type 2 error? Why or why not? Okay. All right, so hopefully you've thought about it a little bit and you've got an answer, but I'll answer it for you. So in this case, we could not have made a type 1 error. Okay, we could not have made a type 1 error. You only have the possibility of making a type 1 error when you reject the null hypothesis. Okay, recall that a type 1 error is when we reject the null hypothesis and it's really true. So if you don't reject the null hypothesis, you can't make a type 1 error. Could we have made a type 2 error? Yeah, absolutely we could. Because a type 2 error is committed when we fail to reject the null hypothesis, even when the null hypothesis is wrong. All right, so in this case, it could be a type 2 error if we conclude that Miramar students have a neutral attitude, okay? Or that Miramar students don't necessarily find drinking either acceptable or unacceptable when in fact they do. Okay? So how could we make a type 2 error? Well, because we only sampled 10 people. Recall that having power to detect a true effect when a true effect is present is enhanced when we have a large sample size. So because we only had 10 people, there's a larger standard error. And that difference, recall that we did see a difference because our mean was 5, but we can't be sure that that mean isn't due to error. Okay? If we had a much larger sample, a sample of 100 or a sample of 1,000, and we found that the mean among that larger sample of 100 or 1,000 was 5, we might be much more confident that it's different than a neutral attitude of 4 because our standard error would be much less. And that would have a great influence on the t-statistic that we would ultimately calculate. Okay? So it's possible that we made a type 1 error in this example. All right, let's just do another example of a one-sample t-test. Let's say that we know that the average stress score from Miramar College students is 6.3 on a 10-point scale, where higher numbers mean more stress. But we don't know the variance. We're going to randomly assign 20 Miramar students to meditate for 30 minutes a day. Then, after 1 month, we find out that their stress score is 5.8. We want to know whether this intervention has been successful. Do Miramar students who meditate have lower stress? Okay. Now, keep in mind, we're not trying to answer this question about these 20 students, okay? Because their mean is 5.8. 5.8 is less than 6.3. What we're trying to do is make a conclusion about all Miramar students who meditate. That is, would it be effective for everyone? So we're not trying to make a conclusion about just the 20 people in our sample. We're trying to make a conclusion about all Miramar students in our population based on the 20 people in our sample. So here's how we do it. We follow the same steps of hypothesis testing. First thing to do is restate the problem as hypotheses about populations. I think I'm neglecting population 1, population 2, but we can say that population 1, Miramar students who meditate, population 2, Miramar students that don't meditate. Our research hypothesis is that students who meditate have lower stress than those that don't. Our null hypothesis is that students who meditate do not have lower stress. That is, they have the same or even more. Okay, so notice that the null needs to be written as the exact opposite. So it wouldn't be sufficient to say that they have the same amount of stress. We need to take into account that they either have the same or more stress. Okay, so it's the exact opposite of the research hypothesis. I think I got lazy and didn't state that in symbols, but that's okay. Determine the characteristics of the comparison distribution. So we know that the population mean for our comparison distribution is 6.3, but let's just say that student services, the body on campus that collects this information, won't give us information about the population variance or standard deviation. And so we're going to estimate it from our sample variance of the people that meditate. All right. And it looks like I've done something very tricky here, which is instead of giving you the variance, I've given you an estimated standard deviation. Okay, an estimated standard deviation. And when you're doing the homework from the book, by the way, keep in mind what's being given to you in a problem. If you're just given some of this information, are you being given a variance or are you being given a standard deviation? All right, so we need to figure out what is the estimated population variance, and then from that estimated population variance, we'll use that to figure out the standard error of the mean. Okay, so in determining the characteristics of the comparison distribution, we know that the mu is 6.3. We're going to come up with an estimate of population variance based on our estimate from our sample. So we're given an estimated standard deviation of 2.5, and we're going to just assume that we calculated this in the unbiased way based on that n-1 correction. And then since we're dealing with a sample rather than individual score, of course, we're always using a distribution of means. Okay, so the first thing that we're going to do is say, okay, I was given a standard deviation, not a variance, so let me get a variance by just squaring the standard deviation. Okay, sometimes I do these little tricky things just to see, the extent to which you're kind of paying attention and tracking the relationships between standard deviation and variance. Okay, so we're going to take that standard deviation and square it to get a variance. Once we do that, we're going to use rule 2a to get the variance of the distribution of means, and then we'll use rule 2b to get the standard deviation of the distribution of means, otherwise known as the standard error. Okay, so same steps that we're familiar with. What's our cutoff for rejecting the null hypothesis? We predicted a reduction in stress, so we're going to use a one-tail test. Our degrees of freedom are 19. Why 19? Because we had 20 students, so n-1 is 19. Our alpha level, okay, in other words, our significance level is 0.05. And then again, one-tail test. So all we do is we use our t-table, one-tail test, alpha 0.05, degrees of freedom 19. So we're going to use a critical value of 1.729. All right, now let's think about this. We predicted a reduction in stress. So what side of the distribution do we want to be looking on? This side or this side? In other words, do we need a positive 1.729 or do we need a negative 1.729? Think about it and make your guess. All right, here we are. We're going to use a negative 1.729. Why? Because our one-tail test predicts a lower average than what the null would suggest. Okay, the mean stress score for students that don't meditate is 6.3. So our distribution of means would be centered around 6.3. Okay, so we're going to be interested in means that would be on this side of the distribution because they would have a reduction in stress, lower stress. So whatever mean we get, when we convert that mean difference to a t, that t-score needs to be more negative than negative 1.729. Okay, so let's figure out our sample score. Again, same as before, except instead of a z-score, we're going to get a t-score. Okay, so it was given in the problem that among our sample of 20 students that did the meditation, their stress score is 5.8. We're going to compare that to the known mean of 6.3. This is the standard error that we figured out. So our t-score is negative. Notice that our numerator is negative here because 5.8 minus 6.3 is negative. Very important that our sample mean is always that first mean. So our t is negative 0.89. What's the interpretation? Our sample mean deviated from the expected mean of the distribution means by 0.89 standard errors. Okay. My animation is still screwed up. All right, so let's decide whether we reject the null hypothesis. Same as before. Here was our cutoff score. Because we calculated a t of negative 0.89, we're going to fail to reject the null hypothesis. Why? Because this t is not extreme enough. It did not exceed the critical value in the expected direction. Let me just get all my animations here before we go into this. Okay. So again, here's our population of people. These are Miramar students that don't meditate. Average stress 6.3. We figured out an estimated variance. Okay. This is our distribution of means. These are the means that are likely to occur via a random sampling process centered around 6.3 with a standard error of 0.56. Here's our sample. These were the people that did our meditation. Their mean was 0.58. The thing is, what we determined is that you could get a mean of 5.8 from 20 randomly selected students, and it would land there, which is not improbable under the null hypothesis. In other words, there's nothing special about meditating in particular, because you could get 20 other people that don't meditate, and you could get a mean of 5.8. That would not be uncommon. Okay, so that's why we're going to fail to reject the null hypothesis in this case. All right, so what's one reason we may not have detected a treatment effect? Okay, this is a really good thought exercise in preparing for the types of questions that could be on the exam, but it goes back to influences on statistical power. Recall that some of the factors that influence statistical power would be the size of the effect. Okay, so one reason is that, well, our meditation might not have been that effective. It lowered stress, but not by a large enough amount. So if we would have a bigger difference between our sample mean and the known population mean, that could have been a way to detect a larger treatment effect. What's another reason? Well, our treatment could be effective, but we had a small sample. So if instead of having 20 people, we had 200 people, that would really change what our distribution of means would look like. Okay, think about the influence on standard error. Standard error, we calculate this standard error by taking the variance in the population divided by n. So we're going to get a much smaller number dividing population variance by 200 as opposed to 20 as we did. Okay, so that standard error is going to make, that reduced standard error is going to make this distribution a lot more narrow. Okay, you can think about kind of squeezing in the sides, in which case our sample might have fallen in the critical region if there's less error in this distribution. So another big reason that we didn't detect a treatment effect is because we've got a small sample size of 20, and if we had a much larger sample size, there'd be less error in the sampling distribution, and we'd have a greater chance of concluding that that same mean difference is statistically significant. All right. Okay. Other factors that could come into play would be alpha level. Okay, so we could have used an alpha level that would be associated with an alpha of 0.1 instead of 0.05. we use a one-tailed test. That would give us a better chance than a two-tailed test, so it can't be that. So probably the main reasons that we didn't detect a treatment effect is the size of the effect as well as the sample size. There we go. Oop. All right, and just the last slide that I want to review is really going over notation. So there's the notation continues to build, and there keeps being more of it. You'll notice just how similar all of the symbols look. So they look very, very similar, but there is important differences between all of these symbols. What you've got in the top set of symbols are standard deviation, and you've got the bottom set of symbols are variance. So basically there's a one-to-one where you've got the standard deviation and then the variance for each of our terms. But what we've got here is sample standard deviation. So this would be the first way we learned how to calculate standard deviation based on the sum of squares divided by n. Population standard deviation sigma. The new term that we have in this lecture, which is the estimated population standard deviation, okay, and the parallel term would be the estimated population variance. Okay, so this is just based on the sum of squares divided by degrees of freedom. Same thing, sum of squares divided by degrees of freedom. And then here we've got the standard error of the mean as well as the variance of the distribution of means. The only difference between S sub m and sigma sub m, or between S squared sub m and sigma squared sub m, is that we've just calculated this number based on an estimated population variance instead of a known population variance or standard deviation. All right, so a lot of symbols. As you're doing your homework, I really strongly advise that as you're using formulas, write out the formulas and use the notation. It really helps when doing the exam to make sure that you can recognize the symbols and the notation. And a good way to do that is just to practice writing out the full formula in your homework instead of just plugging in numbers. So that's my best advice. Okay. This was a lecture that had a lot in it, but really we're still just following the same steps of hypothesis testing, but we've just added a few new concepts. So make sure that you go back and review. Again, this lecture is not meant to be a substitute for reading. It really is just meant to help supplement and clarify what is in the textbook. So please make sure that you're continuing to do your reading. And I will be back with another lecture soon.